So earlier on we looked at some of the definitions and also the introductory part as far as the signal flow graphs are concerned. So now I want us to look at how do we construct signal flow graphs. So from maybe a small block diagram so that we can understand further. Then also we can also look at the analysis of the Mason's gain formula, and later on we'll be looking at the examples on how this one is how we can get the transfer function from the signal flow graphs. So that is what we are going to look at. So we are going to start by looking at the construction of signal flow graphs. Then from there, we will look at how we can develop signal flow graph from the canonical block diagram, so that we can see that, and then maybe form some equations, having some simultaneous equations. We can use that in order to come up with the signal flow graph. So basically, when you talk of the construction of signal flow graphs, then considering that the signal flow graph of a linear system, considering signal flow graph of a linear system, it can be constructed by direct reference to the block diagram of the system. And in this case, each variable of the block diagram becomes a node, and each block becomes a branch. So we can consider this by, let's talk of a signal flow graph. Let's talk of a block diagram whereby we have that, then we have this, then we have, of course, here can be R of S, then here we have E of S, then here we have G of S, then we have that coming to H, also H of S. Of course, we can consider the feedback to be positive or negative. Of course, then that one is now the direction. So if we look at this, of course, this is C of S. So if we look at considering that, then we can always develop, we can construct a signal flow graph for this, whereby we can talk of at each and every point where we have a change in the signal, then we can consider that one to be a node. So we can start by considering an input node R of S, so that here we have an input node R of S. Then after that, we have the next node we can talk of E, because at this point there is the summation, there is some signal that comes from the output, and it is fed at that summation point or the error detector, and therefore at that point we can have E, we can call that one E, can call it E, we can talk of it as E. Then at that point, later on we'll also see that when you talk about summing point usually has a transmittance of 1 unity. Summing point has got a transmittance of unity. Therefore, at that point between the node R and E, we have a gain of 1. Then after that, we can talk of the other node, which is G. We have G here. We have G there. Of course, the gain of G. And then here we have C. And if you remember what we talked about as far as the output node is concerned, then the output node cannot have an outgoing signal, especially if you are the one who is carrying out the construction, then the output node should not have the outgoing signal. Therefore, you can find H. H comes from C here and back, and therefore that is where we have the H, and it will be taking positive and negative H in that manner. That is where we have that, and therefore to ensure that we come up with what we refer to as the perfect sink, and the perfect sink is just an output node that has got no outgoing, so that we can have C prime. We can have C prime there, and again the perfect sinks, just like the summing point, usually have a gain of 1, and therefore from there we shall have constructed a signal flow graph from a block diagram. So this is the signal flow graph of a canonical block diagram. So you can see that the sign minus or plus of the summing point is always associated with H. So that is the simplest way by which we can construct a signal flow graph. So later on, again, under this topic still, we will still talk about having a block diagram. Then from the block diagram, maybe a little bit complicated block diagram, then we change it to signal flow graph, then use the Mason's gain formula in order to determine the transfer function. But that one will come later on in this topic. So it will be the last tutorial under the signal flow graph, where we'll be changing the block diagram into signal flow graph and then using the Mason's gain formula or Mason's gain rule in order to determine the transfer function. So I want us to look at I want us to consider some of the equations, the equations. I want us to now consider equations and use the simultaneous equations in order to develop a signal flow graph. So let's look at that, and then from there we can see how we go on. So consider the following equations. So consider system described by the following set of simultaneous equations. Consider a system described by the following simultaneous equations. The first equation, we can have node x2. We can talk of x2, the equations describing x2. x2 is given as a21 x1 plus a23 x3. Then we can talk of x3 as given as a31 x1 plus a32 x2 plus a33 x3. Then we can have x4, which is given as a42 x2 plus a43 x3 x3. So looking at these equations, I want us to develop a signal flow graph for this equation, so that we can look at how we can develop, because we said that we can always develop signal flow graphs from simultaneous equations. And remember, we talked about what we call the rules. There is the transmission rule, there is the multiplication rule, and also we talked about the additional rule. So, and when we talked about the additional rule, one thing that I want us to remember is that we did say that the value of the variable designated by the node equals the sum of all the signals entering that particular node. So if we talk of x2, if we say that this point is where x2 is, then the value, these sums, they converge at x2. So therefore, we can say that if this is where x2 is, then it means that we can have an x1. For this one, there is x1, then from there, so we can talk of x1 there, and then the gain will be a21. 2, where it is going to, 1, where it starts from. So that one is able to give you a direction. The other one that you can see is that we have a23 x3, which means there is x3, but now there is an arrow. So we can know there is an arrow. The arrow is moving down, moving backwards. That's because we can see that it starts with 2, so it is a2 3, because it is heading to 2, so 2 becomes first, then starting from 3 follows. So with that, we shall have drawn the signal flow graph for that first part. Then we can look at what is there in x3. So x3, so we can have a node x3 here. So if we have the node x3 there, then the first one we have 1. It means that this one comes from x1. So it comes from x1 and does not go through x2, so it goes up there. Then this is now x1. Then here we have a going to 3, where it is going to, and then where it is coming from. So we have A31. So that is the first part. The second part, we have A32. A32, which means X2. So it comes from X2, then directly to that, so that here we have A32. Then the first one, the last one, we have X3, and then it is A33, which means it is a self loop, and therefore here we have A33. And with that, we shall have obtained what happens at X3, the sum of what is happening at X3. It comes to that, it is this, and it is that. All those particular branches converge at X3. And then we can also have X4. So we can have X4. Let's have a node for X4. So for a node of X4, the X4, if you look at it, it comes from A42, which means that one comes from X2. So we can have X2 here. So A42, moving forward, A42. Then we can have A43, X3. A43, X3. So it means that there is one that comes from X3. And here we have A43. Then these ones are what forms these particular simultaneous equations. And therefore, we can join them. We can join everything, and then we can have a signal flow graph for that particular system with the following, with those simultaneous equations. So in this case, if we join them, we can start with that. We can have X1 here. X1 goes to X2. And at that, we have A21. Then we have X3 here. X3 coming to that. We have A23. This is X3. Then we are through with the first one. So if we come to the second one, at X3, we have A33 here. We have A33 for that. Then here, again, we join that. For this one, we have A32, A32. Then there is something that comes from this X1 up to X3. So we can have something from X1 to X3 here. So that here we have A31. And you shall be through with the first two. So you can come to the next one, where we have X4. So we have X4, where we have A43. So that one, A43, there we have X4. Then again, we have something coming, we have a branch coming from X2 up to X4. So X2 to X4. So there we have A42. And there you have your final signal flow graph for that particular system. And therefore, you have combined the three and have come up with a single signal flow graph for that purpose. So that is the final signal flow graph that you're going to develop. Of course, the direction here should be forward, 4-2. It goes to 4 first, then come to that. Therefore, we have that one as the final signal flow graph. So after getting the final signal flow graph, if you have these particular gains, then the overall gain for this input may always be obtained by what we call the Mason's gain formula. And that is what we are going to talk about next. So let's talk about the Mason's gain formula. The Mason's gain formula, some people usually call it Mason's gain rule. So let's talk about the Mason's gain formula. Or we can talk of it as the Mason's gain rule. The Mason's gain formula. So when you talk about the Mason's gain formula, then it is always used in order to reduce the complicated block bar diagram to signal flow graph and then obtain the Mason's gain rule. And it is always very possible whereby when you talk of the Mason's gain rule, then we are simply getting the control ratio. And the control ratio, we know that from the block diagram, it is given as C of S over R of S is equals to G all over 1 minus or plus GH. Of course, That is what we have. Of course, all these are always in the frequency domain. We can give them the frequency domain, so that that is now what the transfer function, how we will obtain the transfer function. So that is how we obtain the transfer function. And when you talk of the Mason's gain formula, so it is the same thing that we are going to obtain by use of the Mason's gain formula, but now we are going to look at it with a different way. So it is always possible to write with the Mason's gain formula. It is always possible to write the input-output relationship and hence determine the control ratio by use of the SFG, and this is always carried out by inspection, which is always accomplished. You accomplish that by using the Mason's gain formula, which is always given as M is equals to, M is given by sigma of pi, sigma pi dot delta I all over, of course that one is the I all over, and then that one should be the overall determinant. So that is what is the Mason's gain rule as far as or the Mason's gain formula. So this is how we are going to get the transfer function. It will still give us the same thing as this, but now using inspection, and that is what we refer to as the Mason's gain formula. So I want us to define everything that is there. I want us to define what do you mean by pi, what do you mean by delta I, and how do you obtain all this. So when we talk about the pi is the gain of the forward, or of the ith forward path. So we are aware pi is, we said that the pi is just the path gain of the ith forward path. It is the path gain of the ith forward path. It's the path gain for the ith forward path. And what you can see is that they are being summed. So in this case, when you talk of the pi, then we are going to have several paths. Like in our earlier, when we were defining the terms used in signal flow graphs, you can see that in that particular signal flow graph, we had two paths. So in that case, we can have path 1, whereby that means that we are going to have P1 dot its determinant 1 plus P2 dot its second determinant divided by overall determinant, which is this. So this is what we call the summation of Pi and delta I. So each and every path times its own determinant. We'll see how we get the determinant, and that is what the Pi is. So it is the sum. So you have to ensure that you determine all the paths, all the forward paths that are possible in that particular signal flow graph, and multiply by them by their determinant, which we are going to talk about. Then after that, we can define this determinant, the denominator, which is the overall determinant, and this is now what will be given by, this is given by 1, always given by 1 into, it's always given by 1 into sum of all gain, sum of all loop gains of all individual loops, sum of all loop gain of all individual loops. So we are going to get it sum of all loop gains of individual loops. So that is 1 minus that. So you are going to look at the loop gains, individual loop, like how many loops do you have and what is the sum of all this, and that is what you are going to get there. And the formula always alternate, just like the matrix, minus, plus, minus, plus, minus, plus, in that order, until you get to where your particular signal flow graph will lead you to. So the value of M will always be determined by what is present in the signal flow graph. Like if sum of all individual loop, sum of all loop gains of individual loops are present, then you are going to have that. Then if that one, if you add that, then after looking at the individual loops, you are supposed to look at sum of all gain products of two non-touching loops. So we have sum of all gain products of any two non-touching loops, So of course, that is now you add that, and then you go to the next, and that is if you have any two non-touching loops present. If you don't have any two non-touching loops present, then your transfer function will end at that. But if it continues, you can still have 3. So that one was plus, this one becomes minus. So you have sum of all gain products, sum of all gain products of any 3 non-touching loops, of any 3 of 3 non-touching loops. You can simply say of 3 non-touching loops. Then from there we can have that, and it continues. Sum of all gain products of 4 non-touching loops, that is now going to be plus, minus sum of all gain products of 5 non-touching loops, and so on and so forth. And that's where this particular formula will end is dependent on the signal flow graph that you are trying to solve. Therefore, that is the definition of that. Therefore, we can now go to the definition of this. That is the delta I. And when you talk about the delta I, then this is just the value. It is the value of the delta for the part of the graph not touching the ith forward. Not touching the ith forward path. Like we talk about this, when you talk about this path, you are going to analyze, or rather inspect the path 1 and look at each and every part that it touches. Should there be a loop that it doesn't touch, then we are going to get the determinant as 1 minus the product of that loop that it does not touch. So that is how we are going to get it, 1 minus that product. But if it touches all the loops, if a path touches all the loops, then it means that the value of its determinant, like if we talk of P1, the value of its determinant, like in this case, if we talk of P1, and the P1, that is the path 1, the forward path 1, touches all the loops, then it means that its value of that, the determinant 1, will be given by 1. But if in any case it doesn't touch a loop, then it will be 1. That value will be 1 minus that particular loop. Maybe it does not touch, maybe GH, you can talk of G2, H2. So that is going to be what you have. So, but that is just by illustration, but we'll see it better when we'll be looking at the example. And in that case, so we have said that this is the value of the determinant for the part of the graph that is not touching the ith forward. So that is what we talk about. And it is given as the value of the determinant for the part of the graph not touching the ith forward path. And therefore, maybe what we have not defined in this case is M, and M is simply the overall gain of the system. M is simply the overall gain of the system. So that is what the Mason's gain is. So for us to understand it further, we will be looking at an example as far as that is concerned. Formula beta. In our next tutorial, we are going to look at a few examples that are going to enable us in order that are going to ensure that we understand what we are supposed to do and how to obtain the overall transfer function by use of the Mason's gain formula. And that is in our next tutorial, where we are going to look at those examples.